Hi, so today we're going to talk about this concept called partially ordered set. Okay, so before that, let's first begin with a definition on a binary relation. Okay, so we say that a binary relation, okay, we can use anything to denote this binary relation. We can just put a letter R here. Okay, so it doesn't matter. We say this binary relation R. This kind of relation is a relation on some set, right? So we say this on set X. Okay, so this relation is actually a subset, okay, of the Cartesian product of X with itself. Okay, so just X cross X. So that's it. Okay. So although we call this R as some binary relation, but that actually is just a subset of the cross of this set itself. Okay, so that's it. Okay, so because this is a set, right? So it's a subset. So we can have the subset notation for that. So we say that this R will be a subset of X cross X. Okay. All right. So this is a little bit abuse of notation, right? So we want to use this R as a relation to link two elements in some set, right? But again, this R actually it is some set, right? So here it's a mixed use of this notation. Okay, so all right. So normally okay, so we can write, let's say, little x, okay, some element in some set X, okay, has this binary relation with some element Y, X or Y, okay, and we do not write, okay, instead of writing, let's say X and Y, they are in this R. Okay, so this is just a common way of writing this binary relation. Okay, this is also true, but we don't write like this. So this is a easier way maybe to represent this binary relation. Okay, so this is just the tradition. Okay, good. So this is a definition on some binary relation. Okay, let's give some example on this binary relation. Okay. All right, so let's say some set X, okay, so the set that we're interested in, that would be, we can have some elements, okay, let's say A, B, and C, okay, so this R is a binary relation, okay, on this X, okay, then this R has to be some, let's say some subset, okay, of X cross X. So let's say we put, so when we cross X by itself, right? So we simply put all those combinations of those elements pairwise, right? So we have AA, AB, AC, right? BB, BA, BC, so on and so forth, right? So we have all of those. Okay, so that's this cross, right? So you're gonna simply pick some of those to be inside of our R set, okay, subset of that. So to form this binary relation, so let's say we put something like maybe like AB, maybe, and we can put something like BA or BB, right? So on and so forth. Okay, that's it, right? So we can put something to have our own R set. Okay, it doesn't matter. So this is just a subset of X cross X. Okay, so this is a valid, well-defined binary relation. Right? Okay, so So, but we don't write like this, right? So, but instead, okay, so normally we write as, so ARB, BRA, okay, BRB. Okay, so those R's means that those two elements they're in inside of this subset, okay, in this binary relation. Good. So that's the first definition we have talked about today. So the next we're gonna talk about this partial order, okay. So, and we're gonna define the partial order set based on the partial order, obviously. So, okay, so this is the first thing. So the second thing, that's gonna be this binary relation. Okay, so we say that a binary relation. Okay, so some R. Okay, on this set X. Okay, it is a partial order if, okay, for all X, Y, okay, and Z in X, we're gonna have some properties. Okay, so we're gonna have some conditions, okay, to satisfy to make this binary relation to be a valid partial order. Okay, so the first thing, okay, first, this is the transitivity. Okay, so if we have XRY, all right, and YRZ, so those two, they imply XRZ. Okay, so this can have this sort of transitivity, right? So we can transfer those relations to the one when we connect them together, right? So this is the pretty straightforward transitivity. Okay, so the second, that's gonna call it reflexivity. Okay, reflexivity. Okay, so it simply means that any element X or Y or Z, okay, it has this binary relation with itself. Okay, and the third is called anti-symmetry. Okay, symmetry. All right, so what it means is that when we have, okay, XRY and YRX, okay, if we have both to be true, then this has to imply X and Y, they're exactly the same. Okay, all right, so good. So this is the those are the requirements, right, that we need for this binary relation R to be a valid partial order. Okay, all right, so then following that, you're gonna next define the partially ordered set. Okay, so a partially ordered set is a set, let's say X again, okay, with some partial order. R on this X. Okay, and we write this this partial ordered set as this X and R. Okay. All right. Good. So this is definition for a partial ordered set. Okay. And okay, although we have all those properties, right? Transitivity and reflexivity and anti-symmetry, but something very important for us to notice is that in the partially ordered set, sometimes we cannot, so we cannot compare, we cannot always compare two things, okay, inside of a partially ordered set. Okay, if you wanna if you want to always be able to compare two elements in some set, and that's gonna be called a fully ordered set. Okay, so that's not a partial ordered set. All right, so that's something we're gonna define later, or totally ordered set, right? So that's not a partial ordered set. Okay, so good. So before that, let's take a several little examples for us to better understand this partial ordered set. Okay, good. So okay, so for the first example, okay, we're gonna have, let's say, we're gonna have this example in R2, okay, and we're gonna also have a binary relation, right? So let's use this greater than and or equal sign, okay? But we need to define this sign, right? The greater than or equal sign, right? So we know that this sign in R1, but this doesn't have an obvious definition in R2, right? So we're gonna define this. Okay, so this is defined as below. So when we have two elements, okay, in let's say R2, okay, we say that X is greater than Y, greater than or equal to Y, if and only if for both two dimensions, okay, X is greater than Y. So Xi is greater than or equal to Yi for I can be 1 or 2. Okay, so it means that on both two dimensions, Xi is greater than or equal to Yi, then we say that X is greater than or equal to Y. So this is how we define our binary relation here. Okay, so we need some rigorous definition on this. So this is how we define this. Okay, and this set is just the R2. Okay, good. So then this R2 with this well-defined binary relation is a partially ordered set. Okay, and we can even generalize this to maybe Rn, maybe in a higher dimension, and you can just write something like this, right? With from 1, 2 up to n dimensions. Okay, it will be still the same thing. Okay, so this is the partially ordered set. Okay, so and we can have a little picture, okay, to verify this if this is true. Let's say, okay, so let's say we have this. Maybe we should change some to some other letters, right? Let's say this is A and B. Okay. All right. Okay, so now we can use X and Y as our coordinates, axis. Okay, so for example, okay, we can put our point A somewhere like this and put B here. Okay, so you can see that the Okay, so maybe we should write this as, so this is x, right? We have those subscripts, right? So this is x1, this is x2. Okay, good. So, all right. So now we can see that the on the first dimension, a1 is bigger than or equal to b1, right? And also a2 is greater than or equal to b2. Okay. So by definition that we just made, so this a is greater than or equal to b. Okay. And of course, this also satisfies the transitivity, right? We can simply have some other point, maybe let's put our C here, right? Or maybe somewhere here, right? It doesn't matter. So this C1 and C2, we have B is greater than or equal to C, right? So we can transfer or we can transmit this from A to C to say that A is greater than or equal to C, right? And also the reflexivity and anti-symmetry, they're also true, right? Okay, so this is a valid partial ordered set for R2 when we define this binary relation as this notation here. Okay, but something very important, as we just mentioned, it is we cannot always compare two points or two elements in this set, right? For example, you cannot compare something like this. Okay, let's say we have a point D here and a point E here. Okay, so you can see that this is D1, this is E1. Okay, this is D2, this is E2. You can see that D1 is less than E1, right? But D2 is greater than or equal to this is the E2, right? Or we can write in the other way around. Okay, yeah. So and we can see that this is this doesn't satisfy the definition for this binary relation, right? So we cannot compare those 2 points. Okay, so this means that under the partial ordered set, we cannot always compare any 2 random elements in that set, right? We can only compare those partially ordered sets, okay, when they satisfy this partial order, right? So that's something very important, and then that's the key definition, the key intuition of this definition, right? Okay, good. So that's going to be our first example, okay? So and sometimes we can see another very famous example on the partial ordered set. It's going to be the power set, okay, and the containing as the binary relation. Okay, so we're going to argue that, okay, so the power set, okay, so we can, so this, sometimes we use this 2 to the power of x, or sometimes we can write as this p of x, okay. All right, so maybe we can just use this 2 to the power of x to denote the power set. So the power set of some set x, that'll be just the all of the all subsets, right? The set of all subsets of some set x. Okay, so that's the power set. So we say that this power set of x and this containing notation, right? Containing relation to be our binary relation. So this together form this. This forms the partial ordered set. Okay. So 2 to the power of x is the power set. So it has. Okay, so it is the set of all the subsets of X, okay? And this thing here is just the containing or superset, right? So it's the reverse of subset, that notation. Okay, good. So this, it is a partially ordered set. Okay, good. So now we can have a very brief example. Let's have this X, for example, to be A, B, and C. Okay, so the power set of that'll be the set of all subsets, right? So we're gonna have A, gonna have B and C, A and B, A and C, B and C. Okay, and we have the empty and the X itself. Okay, A, B, and C. All right, so you can see that this is a partial ordered set. And how do we see that? For example, when we're using this containing as our relation, we can link those partial orders, this partial order set, right? For example, we can see that this A is a subset of AB, and that is subset of ABC, right? Of course, this empty set will be the subset of everything. So, and B is subset of that, and subset of that, right? Also, B is a subset of this, and that will be a subset of that, right? And the same thing for C. Okay, so this is the we can verify our properties, those three properties, by this. Okay, so this is the another example, and we can also see that we cannot always compare any random two elements, right? So we cannot always do that. For example, A and B, they're not any subset of each other, right? For another example, AB and AC, also we cannot compare between those two, right? So they do not belong to each other. They are not subset of each other, right? So and again, this shows the point that we mentioned earlier. So in a partial ordered set, we cannot always compare any two that we want to compare, right? So it's just we can only compare those in the partial order, right? Okay, good. So how do we, if we want to compare all of those, okay, with some under some relation, so we're gonna define something else, right? So that's called a total order or totally ordered set. Okay. So we say that a partial order, okay, yep. So a partial order R on subset X, it is a total order if it is complete. Okay. So it means that for any elements in the set X, we can always compare using this binary relation R, right? So i.e. for any X and Y, in X, we have either, okay, XRY or YRX, right? Okay. Or maybe both, right? So that's the definition for this total order. Okay? And then we can define the totally ordered set based on this, right? So that's trivial to do. Okay, so and from the previous examples, we know immediately that we know R2, and with that sort of the greater than or equal to sign that we defined earlier, that is a partial ordered set. But in R1, with the greater than or equal to sign, this is a totally ordered set, right? Okay, good. Okay, so that's pretty much, and we're gonna also define another term called a chain of some set. Okay, so let's do this. Okay, so now suppose let's suppose this X again, it's gonna be A, B, and C. Okay, and then we know that previously, we know that the power set and this containing is a partially ordered set. Okay. Okay, so we're gonna argue that we can find some subset of this power set itself. Okay, so that this subset we can totally order that. Okay, it has a total order. Okay, so we can always compare that. So we consider some set, let's call this as A, okay, in this power set. We let this A to be a set with empty set A and B, A, B, and C. Okay, so you can see that in the set A, we can compare all of those, right? So this is a total ordered set, right? Okay, so then we say that this A is a chain of the partial order set. Okay, good. So we can see that there are a lot of chains, right? So let's go back and have a look. So for example, so from empty, right? So we just skip that. So from empty, we always have empty, right? So we have A, B, A, B, C, right? So that's a chain, and of course with empty. So and for another example, B, A, B, A, B, C, right? Or A, A, C, A, B, C, right? So that's another chain, so on and so forth, right? So there are a lot of chains that when we put those together, and we can always compare those, and that's just some subset of that partial order set, right? And we call this as a chain of that partial order set. Okay, so that's just some definition for us to know. Good. So that'll be everything for today's episode. So we covered pretty much on the definition for the partial order set, and this is very useful and interesting notation, some definition to know. Okay, and we also discussed some properties, right, for this partial order set. Okay, good.